Hi there, not too long ago you saw me restoring this little guy, the TM3A AC microvolt meter from Levell. I put a link into the description if you have not seen it. But now it's time to introduce the TM3A's bigger brother, the TM3B. From a functional point of view, the only difference is that the TM3B has an additional bandwidth switch, but obviously there's more to it. The actual meter itself is now squarish, has a proper mirror scale to avoid parallax errors, and is just enormous. Clearly this is meant for serious business. The antenna-style input socket for the TM3A has been upgraded to a proper BNC socket. My device, a lucky eBay find, misses the black socket of the AC output, and judging from pictures of the TM3B, the bandwidth knob is a replacement as the original looked much more like the range switch knob. Those are of course minor things. The big question is if it still works. The usual 4 screws hold the rear panel, but as with everything TM3B, these screws are much larger than the small ones used in the TM3A. At least from the outside, the housing is in a better state than my TM3A. Okay, it's kind of funny to see the same size PCB as in the TM3A, which looks rather tiny in the large enclosure. The PCB itself looks like a newer version, very much more organized and tidy. Not so nice, another PP9 battery, apparently in the early stage of leakage. I'm not quite sure what age it is. The marking on the bottom is 00-03D, whatever that means. Maybe 2000 or 2003? No idea. Since I had planned to bring stuff to a recycling center anyway, I took that battery there without even measuring it. For a first functional test, I connect a bench power supply set to 9 volts to the battery clips and then turned it on. That looks promising. After a slight delay, the needle goes right in between the good battery markings. And yes, just like the TM3A, when selecting a range after power up, the needle goes wild because of all those large capacitors charging up. This is explained in the manual and normal for these meters. It only does these wild swings initially when changing ranges. Later everything is much more settled. So let's feed in 1 volts AC, and in the 5 volt range the needle is at 1 on the lower scale. I'm close to 10, meaning 1.0 on the upper scale when selecting the 1.5 volts range. This is looking good. Just some minor calibration adjustments will be needed. I am feeding an AC voltage of 1 volts at 1 kHz, and the meter is currently in the widest bandwidth setting of 1 Hz to 3 MHz, which is the only setting in a TM3A. But in the TM3B I can select a more narrow bandwidth of 10 Hz to 100 kHz. Predictably, this has no discernible effect on a 1 kHz signal. But selecting the next narrower setting of 10 Hz to 10 kHz makes the needle go a tiny bit below 10. And as expected, on the most restrictive setting of 350 Hz, the 1 kHz signal drops massively. All in all, I think this unit works. And my eBay bargain isn't a repair, but just a restore and calibration project. While the meter is powered from a bench power supply, it is easy to find out what the minimum and maximum battery voltage is according to the markings on the scale. Apparently the minimum is 7.2 volts, which may allow the use of rechargeable batteries. The maximum is just shy of 10 volts. With close to the nominal 9 volts, the needle is still on the high side, so they planned for operating at a slightly lower voltage anyway. I need to have a closer look at that missing banana socket, which means removing the 4 screws holding the front plate. Before getting it out, the battery clip has to be pushed through an opening on the battery compartment. As with the TM3A, everything is mounted to the front plate. The black banana socket isn't missing, it's still there but broken off, just hanging on its wire. Here's a close-up of the label on the instrument. I was hoping to see a date there. On the bottom right, that may be a 45/86, so maybe 1986. Apart from the additional bandwidth switch, the schematics on the TM3A and TM3B are identical, but as you can see from this comparison on the PCBs, my TM3B is much newer. The presence of the additional red preset control on the TM3A dates this PCB as before mid-1978 when it was removed. Both versions use blue Philips electrolytic caps, and the one in the TM3As are still fine. The big 3200 microfarad capacitor is now a Rubicon make. I like how they organized the new PCB layout, especially if you compare those caps going over each other. To be clear, this isn't a difference between a TM3A and B, it's just a difference between generations of the same circuit. If you get a more modern TM3A, it would use the same PCB as the TM3B here, or maybe an even more improved version. The broken socket is unusable, so it has to be removed and discarded. I looked in my pile of banana sockets for something matching in style, but this here was the closest that looks kind of reasonably similar. But tightening the nut is not going to be easy because there isn't any space. In the end, I had to desolder and remove the red socket and the shielding plate to be able to tighten the nut of my new black socket. Now for installing the red socket that also holds the shielding plate. Resoldering the wire that was connected to the red socket. And the yellow wire that connects the black socket to the same ground as the B and C socket next to it. The end result. You notice that the red socket has these ridges while my black socket is smooth. I can live with that. Now for other issues. As with the TM3A, the foam in the battery compartment has deteriorated to some brown powdery gunk. Removing this gunk is messy but relatively easy. The problem is that this foam was glued on, and to get that glue residue off was difficult. With the battery compartment cleaned up, it's time to consider the battery itself. A quick look at the past where I had the same issue. In my Marconi Universal Bridge TF2700, I replaced the original PP9 with a new one after cleaning the compartment and the housing, of course. In the TM3A, I replaced the original PP9 with a PP3 battery. The PP3 is what is nowadays known as a standard 9-volt battery, widely available and used, for example, in smoke detectors and many multimeters. In the TM3A, I actually used the rechargeable nickel metal hydride PP3. Those have quite a bit less than 9 volts. For example, this one contains 6 tiny nickel metal hydride batteries in series. That means after a full charge, the voltage quickly drops to its normal voltage of 7.2 volts. As we have seen, that's fine for the TM3X. Apart from voltage, one must consider the current draw. The much larger PP9 has at least 10 times the capacity of a PP3, and with a relatively high current draw in the Marconi, a PP3 would have a very short battery life. In a TM3X case, the current draw of about 4 mA is so small that a PP3 is feasible. But for the TM3B, I was willing to try another solution. Meet the new PP9 battery. There are kits out there that allow you to build your own PP9. They consist of a frame in PP9 shape that contains battery holders for normal AA batteries. This kit here has space for 2 battery holders able to hold 6 AA batteries each. 6 times 1.5 volts is 9 volts, so why 2 holders? It depends on your demands. You can simply put 12 AA's in them and run them in parallel to get more capacity. But another option is to put 6 nickel metal hydride rechargeable batteries into one and 2 more into the second holder. If wired in series, that gives you 8 times 1.2 volts or 9.6. This is for vintage devices that can't handle 7.2 volts. They would get using a solution with just 6 cells in series. I got this kit here, which comes in several pre-wired variants or as a DIY kit, which is what I selected. I'm trying this out on the TM3B, but eventually this battery will go into the Marconi once its real PP9 is exhausted, and the TM3B, like the TM3A, will use a PP3 instead. In my case, I have some leftover alkaline AA's lying around, so I'm first trying just one holder, which I just connect to the clip using a thermal block. All that I need to do now is load the holder up with AA batteries. And then I did a routine check of the voltage, and to my surprise, it read -9 volts. After some head scratching, the problem is obvious. The kit uses a standard PP9 battery clip like the one that is in the TM3B, but now the clip is used on the battery side of things. This means the polarity has to be reversed. To be fair, the instructions that came with the kit clearly say that, but of course I only looked at them afterwards. Thanks to my thermal block, the reversing is easily done. And now the meter reads positive when the red probe is at the plus of the battery. When putting my DIY PP9 together, I worried that the contacts of the battery holder may short on the metal frame. The contacts are not really recessed, just enough to be flush with the plastic. But not to worry, the inside of the bottom frame contains a transparent U-shaped plastic liner to prevent such accidents. The top frame does not, but it has standoffs that separate it almost 1 centimeter from the top of the battery holder. Some thought went into this design. Nice. Initially I used only one battery holder, but the frame is not properly aligned when doing this. Maybe it would have worked if I had moved the battery holder into the middle and put some foam spacers left and right, but I did not think of that. Instead, I used the empty second holder, hiding my thermal block inside where the batteries would normally be. Incidentally, if you load up both battery holders with AA batteries, there is no space for a thermal block. The thermal block was my idea, and the design of this PP9 assumes you shorten the cables and permanently solder the wires together. The kit comes even with a heat shrink tubing to isolate the solder joints. Proper wiring would make assembly and disassembly a lot faster, but I still want to experiment with different configuration in the future. And speaking of configuration changes, I did one pretty soon after. This melted PP3 9-volt battery that got accidentally short-circuited by a screwdriver while lying on the workbench a day after I put my PP9 together served as a reminder that even alkaline batteries can produce a lot of current, and that PP3 and PP9 batteries can easily be shortened because their terminals are exposed and all on one side. While the kit comes with a car-style 3 amp fuse for that purpose, I had not bothered with it. In any case, 3 amps is still a lot, and I decided I rather want much less worst-case current. Therefore, I added a normal fuse holder for a 200 mA class fuse. All that fits easily into the package as long as the second battery holder is not full with 6 AA's. Putting the assembled battery into the TM3B is easy, but with the foam on the rear wall gone, I needed something to prevent the battery from sliding around. Adding 2 foam strips that I had lying around were just the right thing. And now the TM3B runs again on a clean battery power, which is essential when measuring microvolts. With that done, onwards to calibration. With 12.5 millivolts at 1 kHz in the 15 millivolts range, the DC offset on the output terminals should be less than 50 millivolts. With about 45 millivolts it is, but it does not hurt trying to reduce it further, and by adjusting the bias trim pot in the rear I managed to reduce it down to about 24 millivolts. The next step is to verify and if necessary adjust the input impedance. If you recall from the TM3A video, I skipped that because the manual made no sense. The revised manual makes more sense and describes making a special tool for this purpose, which is described here. Please pause the video if you want to read the section. Now, with 2 meters possibly needing it, I decided to make this tool. The tool, shown here with green background, consists of a 100K resistor in parallel with a 1 nanofarad capacitor. The whole thing needs to be shielded and within 15 centimeters or 5.9 inch from the input terminal. To understand what it does, consider the DC and AC case separately. The meter doesn't actually measure DC, but at very low frequencies the capacitors have a very high impedance and can be ignored. So at DC we have a voltage divider consisting of 100K of the tool and the input resistance of the TM3X, which should be 2.5 megohm. If the input resistance has indeed this value, adding this tool will drop 4% of the signal, leaving only 96% to reach the TM3X. At high frequencies, the capacitors become dominant. For example, already at 20 kHz, the impedance of the caps is 10 times less than the value of the resistors, and so the resistors can be ignored. At 20 kHz, the impedance of the 1 nanofarad cap is just below 8K, and the 40 picofarad cap just below 200K. If you calculate the effect, you get exactly the same value of 4% drop and 96% remaining. The procedure says to adjust the input until the meter shows 500 without the tool, then insert the tool and adjust the impedance trim pot until the meter shows exactly 96% of it, which is 480. In making this tool, my goal was to spend as little money as possible. I started with a 100K resistor to which I soldered a 1 nanofarad cap in parallel. As enclosure, I used the handle of an old toy, and after filling the ends on both sides with epoxy to secure the coax cables, I closed the box. A blank piece of wire connects the shields of the two coax cables and provides more contact area for several layers of aluminium foil to shield the plastic enclosure. I agree this is very haphazardly, but it only has to work up to 20 kHz. The meter confirms there is continuity on the shield and across the 100K resistor inside. Later you will see that I put the whole thing into an additional heat shrink tube. The test for Rin uses a 200 Hz signal at just 15 microvolt, a value so low that I have to use my second attenuator you see below the TM3B, as my signal generator do not support such low values. After adjusting to 50 on the lower scale, I inserted the tool, but at the output of the step attenuator. That produced an overload deflection. Realizing my mistake, I inserted directly at the input with less than 50 cm distance. The value is now less than 500 and slightly unstable, but I decided that it's close enough to 480. Repeating the test, but now at 20 kHz for C-in. After inserting the tool, this time at the right place, the display value drops, and I decided again it is close enough to 480 to not bother adjusting. Since the TM3A video skipped the Rin and C-in, I'm using this opportunity to do these tests for the TM3A. The F-type input connector on the TM3A is not really up to hold the relatively heavy cable, and the meter is a bit fluctuating, but I think Rin is close enough. The C-in readout on the TM3A is a tad lower than it should be. In trying to adjust, it is again one of those controls where touching it with an alignment tool is enough to change the reading, so one has to do it on a trial and error basis. But in the end, I think I got it pretty much nailed. Back to the TM3B. The 50 mV range reads a little low, which can be corrected by increasing the amplifier gain. Changing gain means an overall cal in all other ranges is needed, since gain affects everything else. Well, it can't be helped, so here it goes, but I'm showing this boring process a little faster as it's a repeat from the TM3A video. With a careful adjustment of the gain, the 50 mV range now reads correctly. This also fixes the ranges lower than 50 mV. Next is doing the cal for the 150 mV to 5V range using 1V in the 1.5V range and adjusting the 40 dB trim pot in the back. The camera is at an angle to the meter, so due to the parallax error, the needle appears not to align with the number 1. Same when adjusting the upper ranges using the 10V in the 20V range. And 100V in the 150V range reads just fine. Now, being calibrated, I did measure the bandwidth taking into account the 4 possible settings of the bandpass switch. It is notable that the upper limits listed on the bandpass switch correspond pretty much accurately to the 3 dB points. In other words, measuring for example something with a switch set to the 10 Hz to 10 kHz position which is the light blue line in this graph, does not mean frequencies of up to 10 kHz can be measured. Far from it. If one really wants to know accurate voltages, the useful frequencies are limited to between 100 and 1 kHz. The point is, the bandpass is designed as a noise filter, and that starts to bite and reduce the signal well before the upper stated frequency, and still somewhat after the stated low frequency. On the highest bandpass setting, which corresponds to the TM3A, the 3 dB point is at 3 MHz, which is exactly as stated in the spec. From about 30 Hz to 100 kHz, the level is practically linear, which means this is a useful range for accurate measurements. One more thing to mention while talking about the bandpass. I decided to replace the non-original knob for the bandpass filter with this chicken head model. Not because it's vintage looks, but it's much easier to see from a distance what setting is selected. Finally, to clarify one thing, the TM3X meters are not true RMS. They are showing a rectified average voltage, but are calibrated to show the value of a sinusoidal RMS instead. This is true for sinusoidal voltage only. In fact, mathematically, the RMS value of a fully rectified sine wave value is 1.1 times its average. So non-RMS meters like the TM3B and the Fluke 27 on the right here are calibrated to show 1.11 times more than the actual average voltage. It is easy to reveal this trick by switching to a square wave of 50% duty cycle and 2 volts peak-to-peak value. In this case, the true RMS value is equal to the average and mathematically exactly half the peak-to-peak value, or 1 volt. This is shown correctly by true RMS meters as the red multimeter on the left, but the TM3B and the Fluke 27 internally also get 1 volt average, but then mistakenly apply the 1.11 factor and therefore show 1.11 instead. For more on this, I provide a link to a couple of videos explaining true RMS. For other waveforms, or indeed mixtures of waveforms, the average and RMS values can be quite different, which is something to keep in mind when using non-RMS meters like the TM3B. They are really made for nice sine wave inputs. Please contact me if you have an interesting piece of equipment that you want to send in for review or repair, or if you want to donate it to the channel. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.